Okay, so our second talk today is by Nigel Mottram from Strathclyde. He'll speak about process-driven active nematics.
Okay, thanks very much, and thanks for the invite to come along. It's been a very interesting meeting. I'm going to talk about active pneumatic systems. We've had a few talks about those kind of systems before, so I won't do a lot of introduction to either the word pneumatic or active, just a little bit. This is work I've done together with Josh and Geoff. Josh is in the audience over there, so any questions? It's mainly Josh's work. This is a big chunk of his PhD, so any questions, I'm sure he'll be able to answer them. Okay, so just a couple of acknowledgements before I forget. In terms of funding, it's EPSRC doctoral training, partnership funding, and a discipline hopping fellowship when I worked at a very nice place up in the north of Scotland, the Scottish Association for Marine Science, looking at some of these models and how we can apply them to things that live in the ocean. Okay, so what's a kind of general idea here? So we've been looking at active flows for a while, but of course this conference is about design and optimization, so I thought I'd turn it towards how we might design this kind of fluid flow system. What I'm going to do is talk about a really simple model. I am a simple theoretician. There's some very nice simulations, very nice experiments we've already seen. I'm going to break it down to a very simple model and look at some fundamental modes of operation and how we might select those modes. So what we're going to have is a channel of, this dark blue here is the active pneumatic, the active fluid. It's a channel. It's very shallow. So effectively I'm going to think of this as all working in 2D. I'm going to put a top on this, so there's no free surface. So it's really just like a channel flow. I'm going to drive it either internally because this active fluid is going to swim and it's going to move itself along, or I could drive it externally through various different methods, but like a pressure gradient. Okay, so first thing I'm going to look at is what are the steady, or you might call them equilibrium distortions and flow models, modes in that system. Which of those are stable? They can be equilibrium points but be unstable, and it's quite important. Obviously the stable ones will come out in any experiments, but we are able to access some of the saddle point equilibrium. What's going to happen when we do apply some external force, put a pressure gradient on, that's going to select and prefer some of these modes. And also what I'm going to do, I'm going to take some ideas from classic liquid crystal design, cell design, things like imprinting a preferred orientation on each surface, and then seeing how that's going to affect the modes. That breaks symmetries and things like that. And then finally, can we design, using these ideas of applied pressure gradients and preferred tilt, can we design into our system the mode that we're going to select? Okay, so if we just run through a very quick summary of active fluids, if we have isotropic liquids, so isotropic liquids will flow through external influences. We can put on a pressure gradient, maybe gravity, things like that. Normal liquid crystals, what I would call inactive liquid crystals, well, they're almost the same, but they have the ability, because of the asymmetric stress tensor, they have the ability for internal molecular order to drive flows. Okay, it only does this transiently. As it goes to equilibrium, flow will dissipate and disappear, but it has the ability to cause what's called backflow. A molecular rearrangement will induce a flow. When we go to active liquid crystals, well, we also have that backflow ability. They are pneumatic-like, they have a molecular orientation structure, but of course these are like living organisms or microtubules. They have some internal energy source that can cause a kind of swimming motion. So that internal energy source can drive a flow. Okay, so this means they normally swim. So we can think of this, we've seen some very nice pictures of bacteria flowing and swimming. We can go higher up the length scale, phytoplankton. So I looked at some systems of phytoplankton when I was at the Marine Science Association. We can go even further to zooplankton and eventually to fish. I'm not going to model any of that. They swim in very different ways. But the idea is that maybe some of the models with some adaptions could be taken to this higher level. Okay, so this is one picture. I don't know if you've seen this conference, but it's always gets shown every so often. So it's a paper here, and so these are these systems just naturally flowing. This is excited with a magnetic field actually in one place, but you get this very complex behavior, although you can see the same kind of structures. You get this defect, formation, annihilation, periodic pattern. Okay, I'm not going to model something that difficult. What I'm going to try and look for is some of the almost like the eigenstates here, the modes that are happening in there in a more complicated, larger system. I'm going to reduce it down to a very small system. Okay, so I'm going to use a continuum hydrodynamic model, very classic model now, and it's going to be based on nematic liquid crystals. So nematics are, one system is a rod-like molecule, and these rod-like molecules like to align in one direction, and therefore there's the stress tensor is asymmetric, and you can have lots of very interesting effects. When these are active nematics, then we can think of these as either extensile pushers. So this nematic-like rod here, we call it a director. Along that director, this organism likes to push the fluid out along its axis, either end, and pull the fluid in from the side. And the alternative is what I call contractile or pullers, and they pull the fluid in. They pull the fluid in along their axis and then eject it along their short axis. Okay, so two different types. The behavior actually, although it looks like there's some kind of symmetry here, the behavior is very different when you put them in a system. And we'll see that when I show you the modes of operation, as it were. Okay, so these, as we've seen, that previous slide, there's long-range collective ordering here. Well, nematics themselves have a long-range collective ordering, but also there's ordering in the flow as well. There is, as I said before, continuous energy production. That's going to be put into my model of a nematic liquid crystal. And so these are out of equilibrium situations. They can still have steady flows, but it's always continually generating energy. And then they generate forces on themselves and on the surrounding fluid. Okay, so what I'm going to use is the simplest model I know anyway of this kind of active nematic, and it's an adaptive Ericsson-Leslie equation. So Ericsson-Leslie, if you haven't seen them before, the Ericsson-Leslie equations are just the Navier-Stokes equations with essentially a balance of angular momentum as well as the linear momentum. We need angular momentum because our molecules are rod-like and they can rotate, and that there can be a transfer of momentum through angular momentum. Okay, so we're going to adapt that in a very simple way. So this kind of model has been used before. Some of the earliest models in the well over 10 years ago now. What they saw was these two papers very similar in what they saw, and they led in different directions, but what's called a Friedrichs-like transition. So the Friedrichs effect is an effect on inactive liquid crystals where our molecules are aligned in one direction by some force, and if we apply a magnetic or an electric field, that can reorient our molecules. It's exactly the same here. What can happen is we start out with all our organisms pointing in one direction, and if we tweak the activity, we start them swimming faster and faster, they can suddenly reorient. Okay, so it's a Friedrichs, I would call that a Friedrichs-like transition. Okay, so some of that was found in these early papers. What we're going to do is look at this system, and actually what we find are different modes from these original papers. Okay, so the key parameter here that I'm going to use a lot is this parameter. This is my activity parameter. It can either be negative or positive. So in some papers, this is positive and this is negative. It really doesn't matter. You put a minus in front of it and that's absolutely fine. But for me, these extensile pushers have a negative order parameter and the contractile pullers have a positive order parameter. Okay, so what we're going to do is add on one term in the stress tensor for the Ericsson-Leslie theory. And here it is. What we would have is our stress tensor is the classic nematic stress tensor for a liquid crystal. That itself is composed of your normal isotropic fluid stress tensor plus some stuff to do with the fact that we're a liquid crystal. And then we're going to add on this term here. So this term really just, n here is the long axis direction. Well, it's the average of a lot of these organisms, long axis direction. And this causes activity. If you just imagine Navier-Stokes, we're going to put this stress tensor into our linear momentum, and we're going to take a gradient of this stress tensor. You can almost immediately see that zero flow is not a solution of Navier-Stokes anymore, because as soon as I get some distortion in my director n, then it will generate some flow. We'll see that in the equation in a minute. Okay, so this is the simplest term that's got the right symmetry, and there are other terms. I've got an apolar system here. For polar nematic, active nematics, there's an additional term as well you can add in. Okay, so one other thing which is important for people who know about the liquid crystal side of things, I'm going to look at flow aligning organisms. If I shear my organisms, they will reorient to a certain angle within that shear flow. Okay, there are other types, and there are tumbling organisms where, as you shear, there is no stable state and it just keeps tumbling around. Much more complicated. You do get similar kind of effects, but a far more complicated thing to look at. Okay, so here's my system. Here's my channel. I'm looking down on my channel now. All my active nematic system is going to be within this region, and it's going to flow. It can flow up or down. It can flow all over the place. My Z direction is across the way, across this stream, and X is along. If I put a pressure gradient on, I'm going to go along the X direction. Okay, the flow is going to be in the X direction only. Remember, I'm shallow, so I don't think about flow into the board here, and I'm constrained. So as long as I only think of my variables depending on Z, I'm not allowed any circulatory flow. So as I said, very simple system. The director across the director angle here is theta, which is the angle my director, these rods, makes with the x-axis, the vertical direction here. And again, it might depend on time, it might depend on this coordinate across the transverse direction. So as I say, they both depend on just Z. I've got fixed orientations at the side. So here you can see this director with respect to the x-axis. The angle here is 0 on both sides. I will be changing that. I can change that as boundary condition. The simplest is using these Dirichlet boundary conditions. Changing the boundary conditions does change the eigenmodes, of course, but I get some similar kind of behavior. And we might impose a pressure gradient in the x direction as well. Okay, so I'm imagining my fish swimming in my shallow channel, or alternatively my little bacteria, probably more realistically my bacteria. So the flow could be like this, could be in this direction, it could be pointing downwards, in which case we'll see the director structure react to that, and effectively just as a mirror image. It could also be two-way. So I am going to be able to design my system so that I get two-way flow of my bacteria. Of course, this system here will have mass flow. The active nematic will, even without putting a pressure gradient on, the active nematic will cause a mass flow of my system, whereas in this case, there won't be any mass flow, be zero mass flow. I might want this one. In fact, I'm going to think about designing in mass flow, the flux here. And of course, this might be the other way around. And again, I can manufacture that in my system. Okay, so in terms of the Ericsson-Leslie, I'm not going to go through the derivation of these. The key thing here is that I've got a variable theta, which depends on my spatial coordinate and time, and v, the velocity, which also, speed, depends on my spatial coordinate and time. These two equations are the angular momentum and the linear momentum, or forms of them. And this really is just the linear momentum in Navier-Stokes equations. Within here, I'm going to see there's a viscosity which we can map to a standard viscosity in Navier-Stokes. These quantities here, I'm not going to go into this in much detail. These non-linear quantities of my orientational angle are actually like viscosities. And these alphas here are the Leslie viscosities. This g of theta here is the effective viscosity of my material. Whereas M encodes the kind of rotation and stretching of the fluid, and how the viscous dissipation includes that. I won't go into those in too much detail. The key aspects of these equations are that Here I have director rotation. This is simply, there's no mass movement. All my molecules or my organisms here are just rotating on their axis effectively in small clumps. I've got elastic terms. So because I'm thinking of a shallow channel, my organisms stay within a plane. And so if you know about nematic elasticity, what I've got here is just K1 and K3, splay and bend. They're the only type of distortion possible. And I've kept it in both K1 and K3 in here. I'm not going to look at detail about them varying, but we could do that. There's a coupling here. You can see this is a theta equation, but here's my gradients in V, shear in V. This is how the shear flow disrupts the director rotation. In the other equation, I've got some flow inertia. This here is my viscosity, my fluid, well, the G is the fluid viscosity. This is a kind of classic Navier-Stokes term here. I've also got a director flow coupling, so whenever I rotate my director, when d theta by dt is non-zero, I will induce a flow. And finally, this activity term. This is where the activity term comes in. So here's my activity parameter, and I'll look at that in a little bit more detail. I might also put on an applied pressure, and that would just sit at the end there, as it would normally. Okay, so I can actually, if I neglect fluid inertia here, and in fact that's a very good approximation, certainly in this system, very shallow, Reynolds number is very low. If I neglect this, I can actually decouple this system and write it into one equation, which is a very large equation in terms of theta. There we go. So it looks a bit more complicated, but I'll explain each of the bits here. It's more complicated than it seems actually. What I've got is, because I've all this gunk here, the integrations that come from applying boundary conditions, actually is encoded in these A, B, C and kappa 1. But in actual fact, it's not too hard. What I've got here is a kind of modified director viscosity, a rotational viscosity. That's still pre-multiplying d theta by dt. Oops, sorry. I've still got the same elastic terms, they haven't changed at all in fact. I've got the director flow coupling. Now the flow is kind of already solved for, but that's where this came from. This came from a director flow coupling. And I've also got this activity term. Okay, well let's look at this activity term in a bit more detail. If I just look at this behaviour here, this first term, let's go back a step. Oh no, I can go here. d theta by dt, changes in theta are seeing this term here. And for people who look at Erickson-Leslie models, this is exactly like an electric field term, an orienting field term. So my activity is causing some kind of reorientation of my director, my organism long axis. The difference is it's non-local, so I've got the integral of almost exactly the same, well it is exactly the same term in this second one here. So it's a deviation away from an average. And we'll see actually that there is a Friedrichs-like magnetic electric field effect within this system. What you can see here, the one big difference between this and what you might have in a Friedrichs effect is that this parameter here comes in linearly and not squared. Normally we would have here an electric field or a magnetic field squared. So positive and negative applied fields would cause the same effect. Here it's very different. Positive and negative values of my activity parameter will have very different effects. This term's also, actually, as it does in a classic liquid crystal system, this term also introduces this possibility that our base state, theta is 0, very boring state, might be unstable, and that's the first thing I'm going to look at. So let's look at this constant solution, this trivial solution. If you just imagine, if you put theta is 0 in here, if you know all these parameters, it is a solution. It's always a solution for any parameter values, in fact. So this is the solution. Well, we can take away the flow speed because when theta is 0, there is no flow as well. So it's a very dormant situation. All my organisms are lined up. They're lined up like this because of the boundaries, and there's no flow at all. Well, that is a solution for a large number, a large range of my activity parameter, but actually there's a bifurcation away from that as well. Okay, so there are two different modes that bifurcate away, that lead to an instability of my trivial state. So these two modes, actually they're taken, effectively they're taken from classic liquid crystal Friedrich transition modes. They're not too obvious. Well, the first one might be obvious, the other one isn't terribly obvious. and this Q here is a wave number. There's an infinite number of values of Q. Q depends on the n wave mode number here. Okay, and they both lead to instabilities at exactly the same critical parameter, critical activity parameter. Rather unusual. You'd expect these two different modes maybe to bifurcate at different points, but they're both exactly the same. And I'll show you that in a bifurcation diagram. What we've got inside this critical activity parameter is the elastic constant. You'd expect that. This activity is causing some distortion in your active nematic. So if I had a very low elastic constant, that distortion would be easy to do, and my activity parameter would be low. I've also got two viscosities. That's very different from a Friedrichs transition. You don't have viscosity in there, but that's because I'm causing a flow as well as a reorientation. And critically, I'm going to talk about this in a bit more detail, this alpha 3 term here. Eta 1 is a bulk viscosity, it's a Mijewicz viscosity, it can only be positive. Alpha 3, on the other hand, could be positive or negative. I've also got the channel width, you'd expect that to come in really in this kind of transition, and a mode number. So n could be 1, 2, any natural number. And I'll just look at the first mode. The other modes actually lead to not stable solutions, they lead to saddle points anyway, and higher energy eventually. So I'll just look at the first mode of instability. Okay, so this is our critical parameter. It is equivalent to a Friedrich transition. We're going to see that in a minute. So that will be an electric field induced type of distortion. But as I said, it's polarity dependent. It has a different transition if it was positive or negative. And the critical parameter now involves viscosity. That's quite important as well. These aspects of this are going to help me design the type of mode I want to transition to. So in particular, it depends on this viscosity alpha 3. Well, it's not really a viscosity, because viscosity really can only be positive, so it's more like a viscous relaxation coefficient. So this is one of the Leslie viscosities. I'm going to talk about this right at the end of the talk in a bit more detail. Effectively, what we're going to see is if my nematic, if my organisms are rod-like, then only pushers, this kind of extensile flow organisms, only they will undergo this transition. If I have a disc-like organism, then only pullers will undergo this Friedrichs transition. So there's one immediate way of designing in whether I want to transition in this way. If I don't want to transition in this way, and I'm a puller, I just make sure I'm rod-like, and vice versa. Okay, so we know it transitions. We know the trivial state goes to something else. What does it go to? We've seen the modes. So what these diagrams here show you the type of flow that can happen and the equivalent director structure. The different lines here are actually as I increase the activity. You can also think of this as, it's very similar actually, if I did plotted these as a function of time, the growth of my mode would happen in exactly the same way, in fact. So either way is fine. So what's this in terms of my channel? So here's my channel. The flow here is in this positive direction. So I've got this mass flux, or everything's flowing there. I've got a no slip condition, so it has to go to 0 at the edges. I can flow the other way. That's absolutely fine as well. What changes is the director structure. So the director structure here is that it's a positive angle in half the cell and a negative angle in the other half cell. So I get some tilting into the middle and then some tilting into the middle from the other direction. And that just reverses as I go to the other type of flow. Now these are actually classic types of flow and director orientations you see when you put a pressure gradient onto a liquid crystal. So these are the kind of things we would expect. So just to take away the back, this is what this looks like, and you can see, although this looks symmetric in a sense because the director looks symmetric, the actual director angle is anti-symmetric. And the symmetry of these things is going to be important when we try and force the system and break symmetries.
Question, Nigel,
Yeah.
does that saturate somewhat there?
Yep. So there's what's called the Leslie angle, and so in fact, in any shear, any amount of shear, there is a fixed angle that the director likes to be with regard to that shear. And as the shear gets stronger and stronger, you get closer and closer to saturating. Yeah. Okay, there's another type of flow. So remember there were two modes. and both of those modes could be positive or negative. So there are 4 types of different solutions here. So this next set of solutions are where I have anti-symmetry in the flow profile, but symmetry in the director profile. Okay, so in my channel, I've got flow in both directions, either way. And for my director, it's more complicated to draw here, but the bulk of the cell here is all tilted in one direction. And the opposite is tilted in the opposite direction. Okay? So I've got two fundamental types of solution here. And what I'm going to do is try and plot the phase plane, try and plot the trajectories of how we get to these different solutions using 2 measures. This is an infinite dimensional system. Remember, I haven't just got A theta and A V, I've got theta and V throughout the cell. It's an infinite dimensional system. I'm trying to plot, I can't plot infinite dimensions here, so I'm just going to have 2 different measures. One is the average flow, it's the flux, and the other is the average theta. Now remember, I've got symmetry and anti-symmetry in some of these things, so the solutions will be nicely separated to be on either of the axes. So here's the phase plane. So let me just go through this in a bit more detail. So the first thing to say is that the trivial solution, this is where V and theta are both 0, really boring. That's going to sit here at the origin. That's actually an unstable node. If I perturb away from that anywhere at all, I will flow to a different solution. It can be a stable node if I'm before the critical activity parameter. But as soon as I go past the critical activity parameter, it becomes an unstable node. I've got 2 stable nodes, and these are the ones with positive flux, so the integral of V is positive or negative. So that was these 2 flow modes here. These are symmetric flows, therefore they were anti-symmetric thetas. Because theta is anti-symmetric, it integrates to 0, and that's why it's along the vertical axis. Okay? The blue ones here are the other 2 solutions, where I've got, and they are saddle points, and so the flow is in both directions, either up, down, or down, up, and these are saddle points. They are unstable, so if I am anywhere close to this saddle point, I will move away from that saddle point and eventually end up at my stable node. Transiently, I will seem to be going towards my saddle point, but I'll always eventually go back to my stable node. And I'll use those transients actually when I later try and design a method of actually obtaining this saddle point solution. Okay, so the bifurcation diagram. So this is a slice, a 2-dimensional slice, a single activity of this diagram without all the trajectories put on. This is activity along this axis here. For less negative activities, not past the critical value, I have one single solution. It's the trivial solution, really boring, nothing happens. I pass this critical point, this critical value of activity, and suddenly I have 4 new solutions spawning out of nowhere. These are pitchfork bifurcations. The green line here is this trivial solution becoming an unstable node. So my 2 red, I'm trying to draw it in 3D, hopefully you can see this, but the 2 red solutions there are the 2 stable nodes. So those are the 2 stable ones in red. The question I ask is, if I have a real system, how do I choose between the 2? How do I choose whether I want this mass flux in the positive direction or the negative direction? Okay, so that's one question we're going to come back to. So this is all for negative activities, these are extensile flows in my model. What about positive activities, contractile flows? We already know, in fact, let me go back, this solution here carries on, it's always a solution, it carries on for positive values of activity, and it's always stable. So we know that this trivial solution is stable, and there are no bifurcations away from that. We would have found them otherwise. So are there any non-trivial solutions? Well, yes, there are. There's lots, which is good. But they're rather interesting. So let me go through this one first. So we have a symmetric flow, a mass flux, and these are for different, it's either, you can think of time progressing and evolving into this state, or you can think of activity increasing and getting more prominent. So activity increases and causes this jet-like structure. So largely constant velocity, so almost like plug flow, except for in the middle where you have this jet. The director does something rather strange. This doesn't go to asymptote to the go to the Leslie angle. It goes to pi over 2 minus the Leslie angle. Technically an unstable director, what we would expect in bulk to be an unstable director configuration. So there's one with a jet in the middle. The other possibility is we have jets at the edge. There's no slip here, so it does go back down to 0, but there's a very sharp jet of fluid here. So what we find is these solutions where we have a central jet or these boundary jets and two different types of director structure. In this one here, for a large area of our cell, we've got a constant director orientation. Okay, so why didn't we find this when we did our linear stability analysis? Well, it's because these things here are not connected to the trivial branch. So this is I'm not going to draw the face plane, it's rather complicated, but this is the bifurcation diagram. We do have, so we have, you can see here, 8 new solutions, none of which are connected to our black trivial branch. They've all got fold bifurcations in, that's where they come from. 2 of these are stable, these red ones. 2 are unstable nodes, the green ones, and then there's saddles as well connected to them. So rather complicated. The global minimizer for any of these, any positive activity for all contractile is the trivial state, no flow. But we have local minima of these 2 red lines here. These are the jets at the edge of the regions. So these are local minimizers in our system. They actually have the 0 mass flux. There is a jet in the positive direction and a jet in the negative direction. Well, I'm going to go, yes sir?
You said there's a minimizer, but minimizer of what?
Okay, so the elastic, sorry, if I talk about, I can't, yeah, this is a out of equilibrium system, I agree. There's no minimizer in the total energy. It minimizes the local elastic energy there, yeah, sorry. When I decouple my system, I've almost got rid of flow, and I just start working on my theta equation, which is the orientation. So I always think of energy in terms of that. Okay, so what about designing some of these things? So how could we design some active flows? Well, first of all, when you're designing anything, optimizing, you need some kind of objective. I could pick anything as an objective. I might want a particular flow, the flux of my active nematic. I might want to think about reducing stress on my organisms. So quite often these organisms will react to stress. I might not want those jets, for instance. That might induce quite high stress. So whatever the objective is, we can start thinking about which mode will be good for them. We can't we can affect the activity parameter. What I'm going to assume is I've got an activity parameter. How can I now design the geometry or the and maybe a pressure difference and things like that to get the flow I want? Okay, so what I'm going to say is we're going to imagine we want our active materials to self-propel. So let's say I'm processing, I don't know, I was talking to a company who make biofuel from algae. They want to not put the pressure gradient on themselves. Maybe let's get the active nematic to swim its way out of the reaction chamber. So we might want to have our active material self-propelling, in which case we want mass flux. So can we choose a particular state, whatever organism I'm using as my active nematic? So if my active nematic is extensile, so I've got a negative activity parameter, we would definitely want to have one of these solutions. This has got mass flux, there's a great big flow in one direction. But which one should we choose? Or which one do we choose? Maybe we want it to go in the positive direction. How do I select that solution? Well, maybe it's fairly obvious. If I put a pressure gradient on this, then I'm going to at least initially, select one of these. I could turn the pressure gradient off then, and actually what would happen is it would stay in this solution. So the idea is if I add a small pressure gradient on, we can prefer one of these states. So let's see what happens. So this is just a slice, or actually it's the view from this direction of this bifurcation diagram. When I add a pressure gradient, my pitchfork bifurcation becomes a perturbed pitchfork bifurcation. One of these states now is actually the much preferred state compared to this one here. So I can prefer, So I can prefer this state. I could actually then, once I'm on this branch, I could turn off the pressure gradient and it would sit happily swimming along in this direction. That's one way of designing, adding pressure gradients. What about pullers? What about contractile swimmers? These are difficult because remember the global preferred, or everything, or the flow of the system in a phase plane all generally goes to this. If we are far enough away, we will transition to this black trivial state. So how do we get to these states here? Well, we could, of course, start close to them and we will be attracted to them. But how on earth do I set my system off to be close to this? Well, we can. What we can do is we can actually use pre-tilt, because if you see what this director structure is here, is it actually prefers a positive tilt, a positive director angle. If at the boundary I induce that positive tilt angle, then this state will be preferred. I can also do it with an external orienting field. I don't know whether I'm going to be able to orient my organisms. We saw some work there before where they had magnetic fields. This could be polarized light orientation. However we do it, what we could do is turn on an orienting field to enforce this kind of director structure, this orientation of my organisms, this kind of thing. Once it's on there, if I relax my system, I turn my field off, I go to one of these states. I don't go to the trivial state. That's the key thing. So I can manufacture this bulk flow in this way. Okay, well, the trickier thing, of course, is accessing unstable states. And I can't really access unstable states, I realise that. But can I transiently get close to these blue lines here? These blue lines here, so this one has a zero mass flux. What I'd like is positive or negative mass flux, a non-zero mass flux. So how do I get close to these jet flow solutions? It's unstable. I'm not going to stay there forever, but can I transiently get there? If I can, then maybe I can put an impetus in every so often and pump my system to stay in this system. Okay, so how am I going to do that? I'm going to do that by, again, a bit of physics from the classic liquid crystal display type approach, is by using pre-tilt and orienting fields. I can actually get this director structure in a particular way. How I do is by, on one side, orienting my director in a positive direction, and on this side in a negative direction. As soon as I put on an orienting field, this structure will emerge rather than this structure. If I then relax that, it will transiently go towards this type of jet flow. I could then periodically do that, applying that orienting field, and it will keep it close to my saddle point. Okay, so I can do it with pre-tilt. So this is me simulating this. So this is me having a small pre-tilt, very small pre-tilt actually on each side, exaggerated in this case. I put my orienting field on, I get this structure, I then let it relax, and it stays in this type of orientation. If I'd run my simulation for longer, some asymmetry, some numerical noise presumably, would kick in and actually turn this into my other solution, the actual stable solution. But transiently at least, I stay here. And we see this actually in classic liquid crystal fluid flows. We can use pre-tilt to actually induce what is, in actual fact, an unstable state. So it's possible to actually, what we're doing here is actually pushing ourselves with external force onto what is the stable manifold for my saddle point. The system then flows us towards the saddle point. Of course, it never will get there. And eventually some perturbation in the system will actually push us away and over to the stable point. It might even go to an unstable, so this is now a stable node. Okay, we will eventually evolve back down to this kind of, or maybe even the trivial state. One other way, how do we get a non-zero flux solution for our pullers? Relatively foolproof method of doing this. Not even transiently, how do we get there forever? What we do is we look at this changing the sign of alpha 3. So I go to a biologist or a chemist or whoever and say you change the sign of alpha 3. They would laugh, I'm afraid, because it's very hard molecularly to change the sign of alpha 3. But The principle is there, and one possible way is turning from rod-like to disc-like organisms. So alpha 3 is negative when we have this kind of disc-like contractile flow. But when I turn my organism into a disc and have the same kind of contractile flow, alpha 3 is positive. That means my critical activity parameter is now positive, and I can access this solution. So if I can design my organisms to be, rather than rod-like, to be disc-like, I should be able to access this solution. Okay, so lots of different ways of designing active systems, some of which may be possible, but hopefully some of these rather strange solutions, if any experimentalists out there want to try and find some of these solutions, that would be fantastic. But I'll finish there. Thanks for your attention.
You mentioned at the beginning that one of the modes you found at least was different than what was found before.
Yeah.
Why is that?
Well, because previously they only looked for bifurcations from the trivial state. So the ones that are not connected to the trivial state weren't found. Now, of course, they probably have been found in these large 2D simulations, in a sense. You know, locally they may have found this, but they've not found them as that fundamental mode. But we've kind of extracted out that fundamental mode, the jet solution.
Could you say something about the out of equilibrium nature of the problem? So it's sometimes connecting the text question. It's variational almost?
Well,
that's what I was trying
well,
to
it's constantly being pumped by the internal energy of the organism. So
yeah, so that perturbation effect. So if you switch that off, then you have a purely dissipative system.
yes, that's a classic liquid crystal there.
And so I was trying to understand the deformation away from the solutions when zeta is 0,
Yeah.
and watching the bifurcation essentially as you pump.
Well, I think we're very far from equilibrium in most systems. I mean, the very first, that movie I showed at the beginning, liquid crystals don't do that. Nowhere near. I mean, it's very far from being a classic liquid crystal. Yeah. I mean, you can tune it, I guess. I mean, put in less fuel. I mean, some of these things are fuel.
I understand you're referring to some of these states in relative to energy, as if that was somehow a useful marker.
Oh, I just use that as a measure. Really, a nice, simple measure. I'm not sure energy is a good measure in terms of the system energy, because you're constantly pumping energy in. Yeah.
The modeling with the zeta and this simple model, which is very surprising that this can give, to me anyway. What does that correspond to microscopically? Are the little organisms, sort of moving with constant velocity, or giving constant energy, or what exactly does this correspond to?
In terms of energy, I guess that is constant energy. Effectively, it's that flow pattern that I showed. So, did I have it at the end here somewhere? Yeah. So, this kind of flow pattern. That's the symmetry of this flow pattern is basically encoded in that stress tensor, that extra stress tensor term.
So now I double zeta. What changes with this flow pattern? How shall I interpret the doubling of zeta, for example?
Well, okay. So not only does it have to have this flow pattern, you have to have distortion as well to induce some flow.
Okay.
So this is the local flow, but then if you want mass flow, then you need a distortion as well, because remember it's n cross n in the tensor, which then gets, you look at gradients in that tensor, so you need n to be non-constant. So it is rather difficult to see that, but yeah, you'd get a doubling in the amount of well, yeah. I guess you get a doubling in the rate of change of V.
Uh-huh.
Yeah.
So let's hang on speaker again.